Okay, so my name's Adam. I don't necessarily have HPC background, saying that my primary job at NVIDIA was to help our customers scale neural networks. So when I was hired in 2017, I was working predominantly with our automotive customers, helping them to build perception algorithms. So those algorithms that see pedestrians in front of them, obstacles and other, because that was the main problem that required HPC-style computing. They were training on thousands and thousands of GPUs with millions and millions and millions of images. But since then, the world has changed. It changed significantly. Right now, in every AI discipline, this is just a norm. AI is being used at HPC scales. And my team, because I also manage a European team of engineers that are specialized in various forms of neural networks, are helping customers use them to solve all sorts of problems. And today I'll be talking about neural networks because, in a sense, as the title of the talk says, they are starting to have more and more significant impact on science, not just large language models, but overall the things that we've learned about neural networks to make large language model work, they apply to countless other problems. And today, I don't necessarily want to speak directly about large language models. Everyone heard about GPT-4. I want to talk to you about what makes them work, why they are so successful, and why in every other AI discipline we see similar success. And the reason for that is surprisingly simple. And it's kind of hidden in this graph. So this graph shows you a typical computational cost associated with training, not usage, but training of a neural network across the last decade. So this point here to the left, your left, corresponds to one of the most important neural networks that restarted this wave of progress in artificial intelligence, AlexNet, and some random other neural networks that are semi-representative for the state of AI at that particular point of time. And what you will notice on this graph that the y-axis here is not linear. On the contrary, it's every tick here corresponds to an order of magnitude of increase in total computational budget required to train a neural network. And not only did this trend dramatically outstripped expectations of Moore's law, not only it continued, but more importantly, it has very dramatically accelerated in 2018. And I think I would like to spend a fairly sizable part of this talk trying to answer a question of why. Because if you understand why, it's going to be much easier for you to understand what's coming next. And the why is surprisingly simple, and we understood the why since 2017. For reasons that we don't fundamentally yet understand, every time you make a neural network bigger, and every time you throw more stuff at it, and it turns out that it doesn't particularly even matter what stuff it is, they improve. And they don't just improve by a random quantity, they improve very predictably. Hence the title of this paper, Deep Learning Scalable is Predictable Empirically. So the reason why neural networks were so unsuccessful in the 90s, because we've operated in this low, small data regime, where neural networks simply don't work. I think it's fair to say that small neural networks trained on small data sets don't work. But as we increase their size and as we increase the amounts of data we use to train them, they start to improve, and they start to improve very predictably. So now that I told you that we knew that in 2017, you should be asking yourself a question, why haven't we seen the success that we're seeing today in 2017? And the answer to that is straightforward. At that point of time, humankind didn't know quite a few things. One, we didn't know how to scale those neural networks. So I personally remember being on NeurIPS conference in Los Angeles in December 2017, and no one knew how to train those models faster, because we would add more data into a mini batch and they would explode. But secondly, we relied on human labels. Yes, on human labeled data. And as you will notice, those scales here are not linear again, they're logarithmic, meaning that creating a proof of concept self-driving car is trivial. You could mock it on a laptop in an evening, and it will exhibit fair signs of correct behavior. It will drive correctly most of the time. But for most applications, this is not sufficient. And suddenly, if you want to increase an accuracy of a model from 80% to 90%, you need an order of magnitude more data. To improve it from 90% to 99%, you need an order of magnitude more data. To improve it from 99 to 99.9%, you need an order of magnitude more data. This is a brutal relationship. That is why, I don't know how many of you know, but we have a very large automotive division that is providing self-driving car hardware and software to various vendors, including Mercedes and Jaguar Land Rover. And within that group, we have, I don't know what's the current status, but last time I've been listening to the talks of the director of that group, he was quoting 3,000 people full-time doing nothing but labeling. So sitting 8 hours every day, 5 days a week, drawing bounding boxes and saying, pedestrian, road sign, 3,000 people. 5 days a week, 8 hours a day. This is something you can do for some problems. But in England, I think there are 3,000 give or take radiologists. You cannot take all of them for a decade and just tell them to label. That's not going to work. So the reason why we haven't seen this succeed before 2018 is because we relied very heavily on human labels, but that has changed. In 2018, we, and by we I mean NVIDIA, contributed to that significantly, but the humankind, we've understood that same ideas around unsupervised training that didn't work in the 90s because of the scale of the data sets that we have. Once we throw enough data at the problem, they just start to work. And those are very simple ideas, like, oh, I will remove a word from a sentence. Guess what word did I remove? And by doing that, those neural networks started to work incredibly well. By the way, this is how ChatGPT is created. There is no magic involved. It's an extremely large neural network trained on extremely large data set with an oversimplified objective of, hey, guess what word did I just remove? And this plot at the bottom shows you empirical studies related to the above. Every one of those light blue lines here is a single experiment. Every one of them carried out with a larger neural network and larger data set, and that relationship works like clockwork. And it works like clockwork not just in natural language processing, but in countless other disciplines. So in computer vision, text-to-image, video, mathematics, image-to-text, language, automatic speech recognition, computer vision, everywhere we look, we see exactly the same curves. Everywhere we look, we've started to figure out how to train in an unsupervised way. But it's not just the accuracy that we've gained, because if it was just the accuracy, it would be a sad conclusion to the story, because if you look at this graph, this improvement in accuracy was achieved by throwing 10,000 times more compute at the problem. This is not a trivial increase in computational complexity. So if this was the only conclusion of that research, then we would still get stuck with the same status quo, namely some problems would justify throwing so much compute at them, and most others wouldn't. But fortunately for the humankind, this is not the only thing that happened. It turns out that as we made those models bigger, as we've trained them with, pre-trained them with more data, they became dramatically more sample efficient. So what do I mean by that? So a model that you train to just predict a word that you've removed from a sentence is not particularly useful. Almost no one needs a model that just is capable of predicting a word that you've removed. You need to, after that pre-training stage, teach it to do something useful, like, I don't know, classify movies or summarize text. And that is why neural networks typically are trained in multiple stages. One is called pre-training, the second is fine-tuning. So it turns out that as you make the model that you pre-train bigger, and as you train it with more data, it fine-tunes, it adapts to new tasks dramatically faster. So the green line here shows a fairly sizable neural network for 2018 standards. How many of you have heard about BERT? Yeah, BERT has 370, BERT large to be specific, has 370 something million parameters. So this neural network that is tiny in comparison is about 4 times the size of BERT. And you can see that that neural network, after seeing 100 examples of a new task, cannot do that task yet. Is unable to carry out that task, whether that's summarization or a named entity recognition. simultaneous intent classification and slot filling. For every single one of those tasks, in order to force that neural network to do something new, we would have to create a new data set, organize a team of people that knew what they were doing, and organize some compute for them to be able to carry out experiments, carry out validation, and only after countless iterations that one single problem would be solved. But what happened is that as we made those neural networks bigger, they started to fine-tune, if you wish, faster, to the extent that the largest of the neural networks here, after just single training example, yes, after just single training example, literally one training example, this is summarization, please go and do it, is capable to outperform not only this model after seeing 100 examples, but this model after seeing tens of thousands of examples. And even more importantly, we've started to notice that without any examples whatsoever, the model just does things. So we take the model that we've trained to do nothing but to guess what the next word or the missing word is, and we just ask it, could you please summarize? And I will not tell you how to do it. And despite that, they summarize, they translate. And at that point of time, this wasn't quite exciting yet, because this is, a fascinating academic property. It's not useful at this stage, but what happened in 2022 is that we started to figure out very simple tricks to improve that zero-shot learning capability. So ability of those models to do new things without any training whatsoever. In particular, we started to identify approaches such as prompt learning. Then we started identifying Google in, I think, February 2022, supervised fine-tuning, namely creating tiny fine-tuning data sets consisting of question and answer pairs to explain to the neural network what answering a question actually means. And then reinforcement learning approaches, in this case based on PPO, that showed to the neural network what a good answer constitutes. Those methods are not teaching the neural network anything new. It was trained to do everything it knows at the pre-training stage. We're just saying, you don't know clearly what a human expects when answering a question. This is more or less what you should be telling when someone asks you a question. And that sufficed. So the success of models such as GPT-4, and there are now countless of models that have very similar properties, it's just that we've taken a very old neural network that looks very much the same like the neural networks we would design in the 90s. We've made it horrendously big. We've used some tricks to make it stable at training time, and we've thrown incredible amounts of data at it and asked it to guess the next sentence, next word in the case of GPT-4, or more precisely, next token. And then we've taken a tiny little data set of question-answer pairs, and we told the neural network, hey, this is what answering questions means. From this point on, do it. And that's it. We can now answer questions. And this has quite fundamental implications. So, for example, if you look at zero shot, so again, without any additional training, a problem of generating source code. Human eval is a data set consisting of descriptions of short snippets of code and the code that the neural network is supposed to generate. Like middle of last year or beginning of last year, state of the art was at 30%. So this is super fascinating because humankind never had anything like that before. We didn't have a tool that without training we could just tell to, just write me a piece of software in Python. And it would do it with 30% accuracy, but 30% is not particularly exciting from the business perspective. It's not particularly usable. But within just a couple of months, we've moved to 82% by deploying the tricks that I've mentioned, and now significantly above 90%. We can take a neural network that we've never trained to program and tell it to program, and it programs. And in pass 1, so pass 1 means the first attempt, like the first time you have written the code before you even started debugging it, it achieves quite high accuracy. And this is not just something that happened in software development. Everywhere you look, we see the same properties. So this is MMLU dataset consisting of pre-university, university exams of various shapes and forms, things such as environmental science, art history, psychology, US government, US history, SAT in maths, world history, biology, microeconomics, writing, statistics, microeconomics, uniform bar exam, and across literally all of those problems, once again, in zero-shot setting. So we have never trained this neural network to do any of those things before, and it behaves like that. A lot of you work in academia. How exactly do you calibrate your exams? Where does a medium student land on the scale from 0 to 100%? A mediocre student. How do you calibrate them? It's not 90%, is it? It's 60, yes? 70? 50? Where is it? So notice, this is all, largely above 80%. And I know this is a simplified problem, it's a multiple choice question, but still, we have never trained this neural network to do any of this. That is why many very reputable academic institutions like Microsoft Research are not talking about small incremental improvement to natural language processing, but they are starting to make bold statements like this, talking about sparks of artificial general intelligence. And there is a grain of truth in that. We have never trained this model to do any of that. And we've just asked it to predict the next word. And that is also why we see economic analysis like that, saying that our analysis suggests that with access to LLMs, about 15% of all worker tasks in the US could be completed significantly faster at the same level of quality. When incorporating software and tooling built on top of LLMs, this share increases to between 47 and 56%. So effectively what they are saying is that even if we don't make any further progress and we use the models that we have right now without any additional changes, 47 to 56% of everything that the humankind does will be able to carry out dramatically faster at the same level of accuracy. This is not a minimal incremental impact on humanity. This is, a very sizable part of the economy and very sizable part of science as well. That is why people like Geoff Hinton are comparing the impact on economy of those models to the Industrial Revolution, or maybe even invention of the wheel. And I strongly recommend you watch this CBS interview. It's quite informative. Let's not go through it today, though. But what does it mean for science and industry? So there are some applications that are super obvious, and we've alluded to some of them already. Code development. There are countless of companies whose core business it is to develop software to larger or bigger extent. And the studies that we see already, not studies that we'll see in the future around future tools, but if you take Google or GitHub Copilot and you get a bunch of software developers and you ask them to do a bunch of programming tasks, on average, 55.8% is the difference in speed between the groups that are versus are not using those tools. But this is obviously an average. More skilled developers are significantly less affected by those tools than less skilled ones. But on average, a typical developer that today goes to GitHub and uses their Copilot will write code 55% faster. This is not a quantity that one can ignore. This can make or break business. That is why there are a lot of companies investing resources into the problem. But this also clearly affects research. And you might say, yeah, but that affects only mainstream code development. Those models will clearly not know anything about scientific computing. And that's not true. This is an extract from a talk that my colleague did, a colleague that specializes in geology, and using a Madagascar package, he was able to convince out-of-the-box model without doing any modifications to it whatsoever to generate not only the code to do individual seismic tasks, but actually derive a plan of how one would do an analysis of a seismic image. Internally, we also have some projects looking at Verilog code generation. This is an extract from our paper. So those are not mainstream programming languages. Those are niche disciplines. And this will not just change the way professional software developers write code, but many non-engineering users will suddenly have access to software development. This is a screenshot from quite a good blog talking about OpenAI's code interpreter, a plugin. And in this example, he just uploads a data set to the model and then tells the model, can you tell me the descriptive statistics of the data, and also create some basic charts and graphs that help me visualize what is in it and any patterns it might contain. Boom. Yeah, I didn't like that. Can you modify the top 10 operating airlines bar chart for me? I'd like to see bars horizontal, make them gray for me, please, and can you add data labels to the ends of each bar, making sure to add 1,000 separators. Boom. And you can have a conversation with this tool like you would have with your, I don't know, personal software developer. The main difference is that it has infinite pensions and infinite amount of time for you. And this is not like bleeding edge research. There are products on the market, open source products you can just download. Let's have a look. Yeah, so you can just can clone it. And this is just one example, and obviously it will change search. It's already changing search. That is why, the big search companies are so active in this space, because I think it's clear that the search that we use today is over. Yes, we will in the future no longer just type stuff into the box and get a bunch of links. Instead, we'll have detailed, in-depth conversation about the problem we have at hand. To the point where we might stop having web pages, because you will never click on anything, so why would you have web pages? You might have just like knowledge repositories that you'll make available for the crawlers to parse. And we see already examples of that on the market. And we also see that affecting academic industry. We start to see tools that do the same, but to academic literature, do more systematic, larger literature reviews, analyze and summarize content. And it is not even a new idea. This is a talk that a group that I'm working with at AstraZeneca delivered on our GTC conference. This was actually quite some time ago. This was 2021. So still using the old wave of large language models, if you wish, that were much more difficult to use. But in this case, they just parse through a ton of academic literature on pharmacology, try to identify relationships between chemical compounds and proteins, and they've managed to, just by doing a literature review alone, identify a lot of new targets, and after verification, 1 out of 6 novel targets that they've identified proved to be quite sensible. We'll also manage complex systems with those models as well. This is an extract from a paper from Microsoft that shows how they are experimenting with using those systems to identify failures and root causes. So, hey, model, I have a server that has died and those are the symptoms. What is the likely root cause? It's this. What should I do to verify it? You should conduct those experiments or those tests. And this works. And it's, again, not just some bleeding-edge academic research, but we have a large partnership with ServiceNow that is trying to build tools like that for general population. And it's also affecting, quite hard academic disciplines. So those are just some examples of how those models are forced to do math. Can you prove this problem for me? Sure, why not? And those machines are not generating the most beautiful problems, but I'm sure with proofs, but I'm sure with a bit of convincing, they will make them more appealing to a human eye. Nevertheless, they are correct. And we are already starting to see also specialized models that are not just able to interpret human language, but are also incorporating artificial languages like, Smiles notation, like protein encoding, and so on and so forth. And we're starting to see dedicated, specialized scientific and non-scientific models. Bloomberg, they've just published a paper in May talking about their approach to building financial-centric models. And we're working with University of Florida, to whom one of our founders sponsored a very large supercomputer on building large language models for electronic health records. But again, what I've just showed you are the obvious applications. I think we're right now very much in this situation. Let me look at the time. It's right now asking about applications of those models is like going to a village in the 18th century and telling people, hey, I've invented electricity. And they say, what's electricity? It just makes things go hot. Sometimes it makes things spin. And then on occasion, it also makes it shine or generate light. And so what can you do with it? No one would have come up with this at that point of time. No one. Maybe with some, rare exceptions, Jules Verne, maybe. Most people came up with those things, and those are the things that we are finding. We've started to talk about summarization of literature, research, but what is the future of academic books? Is there a future of academic books? Will books even exist in this world where you can just, hey, neural network, what's the difference between Lars Lark and Adam W. Optimizer, and why no one is using LAM for larger transformer neural network architectures? You can ask that question today, and it will give you a fairly reasonable answer, quoting sources if you need as well. So if you can do that, why would you need processed source of knowledge? If you have a processed source of knowledge. And that's why people like Bill Gates are saying things like, AI chatbots like ChatGPT can replace human teachers. Maybe they can, maybe they can't. But what is important is that Khan Academy is doing a fantastic job integrating those tools into educational utilities for young children. And if you haven't seen it, go to YouTube, type Khan's Academy, ChatGPT. It's mind-boggling how good it works today. And it's not just language. It's sometimes quite easy to forget what I've said at the beginning, that the secret sauce was our ability to do unsupervised training at scale. So we're starting to see this. Much larger, much more comprehensive multimodal systems that can operate on several different modalities at the same time. This is a project that I had a privilege of working on with a company called InstaDeep that was recently acquired by a major pharma company. We've just taken a large language models. We've made minimal changes to it. We've downloaded several different protein DNA databases. I'm not a biologist, so I just helped with the machinery of the process. And we literally masked segments of it, and we've asked the neural network to guess on those data sets. And after we've done that, we've just applied a linear classifier on top of that neural network, and we've either managed to beat, match, or are very closely behind the state of the art by doing absolutely nothing, by just throwing gigabytes upon gigabytes of DNA sequences on a language model. Similarly, in chemistry, I've been helping with a project called MegaMolBART that we've been doing with AstraZeneca. And effectively, we take very large data sets of chemical compounds in Smiles notation. We pre-train those very large models in an unsupervised way, and then we adapt them to solve a wide range of problems in pharmacology. And in longer-term chemistry, if you're interested, there are some good papers that came out of NVIDIA and AstraZeneca on the back of that. And again, this is not just some bleeding-edge academic research. A lot of that is in production. There are a lot of startups that are bringing those systems to the market. If you go to our portal, you can sign up for early access into BioNeMo. You can just use those models. And they are systematically starting to change other disciplines. So if I can represent chemical compounds in pharmacology, couldn't I do exactly the same in material science? Of course I could. So why not just take a material database, ask the neural network to guess a bunch of locations of atoms and see what happens. And people are doing that with great success. Does it only apply to language data? Of course it doesn't. We see exactly the same success in automatic speech recognition. In fact, we've seen it for quite some time. I'll show you a short video of modern automatic speech recognition model and to show you predominantly how many different tasks a single unsupervised model can carry out. And then I'll talk about how it applies to science in a second. Or maybe I will not do it because it's too quiet. So in effect, this single model is unsupervised, but it can carry out a wide range of different automatic speech recognition tasks and text-to-speech tasks. So it can take a piece of text and generate someone's speech. It can take a piece of text and someone's speech and generate speech that is similar to that person. It can take a piece of speech and you can tell it to modify it, and it gives you modified sequence of speech. But this is just a time series problem. So if you can do it with speech, you can do it also with, I don't know, EEG data. There's no difference. You can also do it with sequencing data. And in fact, people do. Like if you look at some papers that came from Cambridge Nanopore, they just use out-of-the-box ASR models to denoise the electrical signals that goes from those nanopores. And obviously images. And we've made tremendous progress in computer vision, arguably as large, if not maybe bigger, than in natural language processing. This was state-of-the-art image generation in 2014, and this was the state-of-the-art in image generation in 2020. And none of those people were ever born. And none of those objects were ever photographed. And we already see quite a few disciplines fundamentally shaken by those models. So initially design is the obvious candidate. So furniture, fashion, architecture, automotive, game development, but already biology, chemistry, material science, scientific visualization as well. And this is a cool example, but I will skip through it. This is an example how we use those models also to collect data, because if those models know how to draw a face, surely they will also know how to identify a face. If they know how to draw a cancerogenic tissue, surely they will be able to find it in a pathological slide without any additional training, may I add, and they do. So this is another paper that we've showed that demonstrates just that. That they not only can be used to generate content, but also interpret the content of the images, and they can do much more than that. They can also do planning. You, neural network, can you help me understand how to grab that object, given the photo of the scene? And it just goes on, and you have to rotate your arm like that, approach it from that angle, and they are exceptionally good at planning. They are quite good at simulation. This is another extract from NVIDIA paper showing how to train those models in unsupervised way to generate new traffic scenarios. But if you can generate new traffic scenarios, you can generate quite a few other physical quantities. You can use them in physics to denoise flow information, upscale it in its resolution. Those are quite more established applications by now. And obviously other modalities that we have never even thought about. I think it's clear to say that there is no reason why those scaling laws shouldn't work in every other AI discipline as well. Sometimes we haven't figured out how to formulate the problem for unsupervised training quite yet. And obviously multimodal examples. This is just an extract from a meta paper showing their approach to bringing quite a few different modalities into a single model. And I want to point out that those multimodal architectures are trivial. You just take a large vision model, large language model, and put a layer in between them and call it a day. So, and we already see practical applications of that. This is an example from Wave that are using combination of signals, images, video for explaining behavior of the vehicle. So I'll start concluding right now. It's clear that we just have 3 minutes left. But what is the role of NVIDIA and all of that? You've discussed our role already. We make those neural networks possible. I think it's fair to say that with some small exceptions, every single one of the models that you see in the TV and that you've heard about today was trained using our hardware. And by our hardware, I don't just mean GPUs, but I also mean our CPUs and our DPUs, yes, and our networking equipment. They were trained and deployed on servers that we've designed, following HGX architecture, and data center designs that we have created that all of the CSPs and many other organizations across the planet are using. More importantly, because of course this is necessary but not sufficient, all of those models were trained with our software. So with our end-to-end platform, so under the hood below PyTorch, tools such as CUDA, cuDNN, Nickel, TensorRT, Megatron Core, and many more. And obviously, a small proportion of them were also trained using our end-to-end tools like NeMo that today provide end-to-end open source toolkit for academia and business to build those models. So if you want to train them from scratch, all of the software tools exist, including all of the hyperparameters necessary to train them. So if your organization wants to train Meta's Llama 70B, sure, you can, as long as you're willing to devote hard work and resources to it. And that extends beyond language models to multimodal architectures and so on and so forth. So let's skip that because we will run out of time. I just wanted to show an example of the tool, but let's conclude with the barriers. So when I deliver this or a derivative of this talk, I typically face barriers. So people say a lot of things. Why do they believe that building those models is difficult or not possible? And some of them are true, some of them are false. So one of the key barriers that people mention is, oh, we don't have access to datasets. But we just download. We just double-click on Common Crawl checkpoint and a dataset, and that's it. Yes, there is some cleaning involved, but largely speaking, those datasets are abundant and quite universally available, and there's no labeling. Not to mention that a lot of organizations like TII already did the hard work at cleaning them. You can just download them. Is it complexity of software? No, because as I've mentioned a second ago, open source utilities to do all of this exist. They scale perfectly linearly. We've tested them on the world's largest supercomputing systems, and we now know the hyperparameters to train those models. Is it the compute? Admittedly, those models are expensive. So if you had a system of 64 GPUs and you want to train 17B GPT on a tiny data set of 300 billion tokens, modern data sets are at least 10 times larger. It will take you a year. So no, you cannot do it on a laptop. Yes. So even if it was remotely possible on a laptop, in terms of software, once you press enter, you would get results about 24 years later. But on a system like that, it's kind of possible. It would take half a year though, and no one else could do anything on it in the meantime. But it is possible, and countless of not just universities, Barcelona Supercomputing Center is a great example. They have an exceptionally good natural language processing group there. But there are tons of startups that are raising money to do it at dramatically larger scales. So with that, I'll open for questions.